Okay, so if you had these three triangles, you could work out the missing side using x squared plus y squared equals r squared. And that's normally the way to go, except for if you recognize you've been given a special triangle. I hope some of you recognize that if a leg is 1 and the radius is double that leg, that's part of, you don't need to do that. Hopefully some of you recognize this was a 30, 60, 90 triangle where this is the 30 degrees. Because in a 30, 60, 90 triangle, the radius is double the short leg. And as soon as you see that, you know you've got a 30, 60, 90. This would have been the 60, and this side would have been the square root of 3. And it saves you a lot of work. And this is a triangle you're going to need to know very, very well. And here's the same triangle, just in a different orientation. This one might have been easier to spot. If your legs are 1 and root 3, then this would be the 30. See, it's been swung around. This time it's your y that's 1, and it's your x that's root 3. It's the other way around for the 1. This is the short leg. Your radius is double the short leg. It would have been 2. Okay? And in this triangle here, as soon as you see that the legs are the same length, I hope you're thinking 45, 45, 90. And you must know these triangles really, really well. And on a 45, 45, 90, the radius, the hypotenuse is the square root of 2. Okay? Now, I want you to be able to draw these two triangles, 30, 60, 90, and a 45, 45, 90, in any orientation, and be able to fill in the side lengths really, really quickly, and to recognize it when we've given you something that's been disguised. For instance, if you had root 3 here and 2 root 3 here, can you see that this radius is 2 times that leg? This must be a 30, 60, 90, where this is the short leg. And this is, the radius is double the short leg. So this would be the other side, and it would be your short leg multiplied by the square root of 3. It would be 3. We can disguise them in all sorts of horrible ways. That would be horrible if you've been doing 3 and 2 root 3. It would be harder to spot. That was about the worst case for spotting that one. It would be much easier if I'd given you something like 2 and 10. And you think, oh, no, not 2 and 10. Sorry, take that back. I've given you 5 and 10. You think, that's double this one. It's a 30, 60, 90. So the other leg must be 5 times root 3 times the short leg. If we've given you a triangle that had 5 and 5, they're the same length. So this is a 45, 45, 90. This is 5 times the square root of 2. Now, I've gone very quickly over that. I know I've gone quickly over it, and you're going to become more and more familiar with them the more you use them. But you must know your basic 30, 60, 90 and your 45, 45, 90. You must know them really well. Okay, moving on. So yesterday's lesson was, if you spotted it, it was to fill in this and to label all those angles in radians and degrees. Now, we're not really hugely interested in the degrees. We really want this in radians. If you haven't done it yet, and you've got the packet of notes, find the white copy, not the yellow one. Use your white copy. And the yellow copy is when you're going to stick triangles all over. If you don't have the packet, stick with me now, and I'm going to pretend I haven't got the packet either, and I'm going to draw it from scratch. What we're going to be doing is we're going to be labeling all of these angles on a circle. There's one in the middle, and these ones here and here, they're not halfway, they're closer to the middle than they are to the edge. They're a third of the way across. They're not equally spaced. Right, so how we're going to do, if you haven't got the printout, you're going to need lots of papers today. Draw your best effort at a freehand circle and cut it into fourths, the 4 quadrants. Now we're going to label these 2 first, then these 2. Then we're going to cut each quadrant in half. I'm going to do the midpoint in each quadrant. And then we're going to go back in and put in the ones that go here, 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 and here. Okay? Right, so just draw a freehand circle and let's start labeling. If the angles are in, if this was the axis, so that's like your x-axis, and this is your x-axis, that's your y-axis. This would be 0 in radians. Anything I draw in the middle, I'm going to erase, so don't copy it. If you're on your neat copy, don't put all my scribblings on your neat copy. The whole way around is 2 pi. Half of the way around is 1 pi. The stuff I'm writing on the outside you do want, but the stuff I'm writing in the middle, I'm going to erase it again and again, write other stuff. So, if this is 1 whole pi, to go half of the way must be half of pi. So this angle at the top, that point, we're going to label that as pi over 2. And let's think about it. If this whole quadrant is half of a pi, this would also be half of a pi, and so would that one, and so would this one. So to go from here to here is 1/2 of pi. Add another half on, and we're at 2 halves of pi, which is the same as 1 whole pi. Add on another one, and we're at 3 halves of pi. Okay, so we've labeled those 4 angles. I'm going to erase all my extra stuff. We have just labeled these 4 angles here. Don't lie in a quadrant, they lie between quadrants. Those are what we call our quadrantal angles. Your quadrantal angles are 0, pi by 2, pi, 3 pi by 2, and all the way back round to the beginning, 2 pi. 0 and 2 pi have the same terminal ray, so this one here. Okay, so we've done our quadrantal angles, and they're very special. Now let's cut each quadrant in half. So I'm going to name this angle, this angle, this angle, and this angle. Now the stuff I'm going to put in the middle, I'm going to erase again, so you don't need to write this. This is just thinking. 180 degrees is the same as 1 pi, 1 whole pi. I have just cut it into 1, 2, 3, 4 pieces. So each piece is a pi cut into 4. This is pi by 4. Or the other way you could think of it is you were at, this point is halfway, and half of a half is a fourth. But in any case, each of these pieces of pizza is a pi by 4, a fourth of pi. So we can simply count them as we go around. We've got order of labeling those now. This is 1 pi by 4. This could have been written as 2 pi by 4, but we kind of prefer the reduced format. We prefer pi by 2. But 1 pi by 4, 2 pi by 4, this is 3 pi by 4. This is 4 pi by 4, which is the same as a whole. So this point here is 5 pi by 4. This would be the same as 6 pi by 4, but we prefer it in its reduced form. And this would be 7 pi by 4. Okay? I'm going to clear up all the extra working I've put on this again. So I'll just clear the junk I've put all over it. I'll clear out all this stuff in the middle. And now we're going to look at these. Oh, I'm going to do those in blue. We're going to look at these points here. They would come from, just kind of fill that. This would come from cutting this into 1, another piece the same size would take me there, 2, 3 pieces. 1, 2, 3. These are actually your 60-degree angles, and in radians there's 1 out of 3, they're 1/3 of pi. So that's pi by 3. So this one would be 2/3 of the way from 2/3 of the way to a full pi would be 2 pi by 3. And then if I came down here and here, this was 1 pi by 3 plus another pi by 3 plus another pi by 3. This one here is 4 pi by 3. Ooh. Okay. And this one over here, that's 4 pi by 3. This one will be 5 pi by 3. Right. While you're catching up, I'm just going to clear all the extra junk off my picture. So what we're trying to get here is we're just trying to get labels for these dots on the outside of the circle there. So I'll clear up all the junk I've got in the middle. Oops, ruined my circle, Okay, now we're on to the last part. We've also got these dots here, 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 and about here. No, I've drawn that badly, it's drawn freehand. Okay, now what these are the equivalent of your 30 degrees. And there's 1, 2, 3, 4, 5, there's 6 of them. 6 30 degrees take you to 180. So these are 6ths of pi, they're pi by 6. Now I could count them, but this is important now. I'm going to show you a totally different way to name this point. Now, I want to move that label over there a bit. In my way. I want to label this one here. I'm going to do it in a different way to how I label the others. The easiest way to get to this point is actually to go the whole way to pi and say, just take this one little piece off. So I'm at a whole pi and I'm going to subtract 1 pi by 6. A whole pi is like 6 pi by 6. If I take away 1, I'm at 5 pi by 6. And that helps me know how to name this one. This one is a whole pi plus a pi by 6, so it's 7 pi by 6. Okay? And how to name this one over here, really have done this badly, it's not to scale. This one would be a whole 2 pi. 2 pi, take away a 6th. 2 pi could be written as over 6, 12 pi by 6. 12 pi by 6 take away 1 30-degree segment, piece of pizza, and you'd be at 11 pi by 6. Okay? So that's what you want. You don't want all this junk in the middle, but you want to have all of those values neatly written on a circle like this. Here were our green ones, and they were pi by 6, 5 pi by 6, 7 pi by 6, and 11 pi by 6. These were pi by 4, pi by 2, 3 pi by 4, pi, 5 pi by 4, 3 pi by 2, and 7 pi by 4. You might have this upside in front of you already. And this one was pi by 3. This is 2 pi by 3. This is 4 pi by 3, and this is 5 pi by 3. Now I can fill that in very quickly because I know it so well, and you're going to have to learn it really well too. So how you learn to do this really quickly is you look for patterns. Okay? So what you want to do, looking for patterns, if you're on your yellow sheet, if you've got the yellow sheet made up, you can put these notes down at the bottom, or you can just put on any sheet you've got, somewhere you've got this nicely drawn out. What we're going to look for is we're going to look for patterns on how to name these. And to do it, we're going to look at the numerator and the denominator separately. We're going to put very simple notes on how to, denominator first, sorry. We're going to look for a pattern in the denominators. And then we're going to look at 4 separate patterns in the numerators by quadrant. So we're going to learn how to fill in the numerator for quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So either looking at mine or at yours, better if you're looking at yours, let's look at those denominators first. Just read them out as you go around the circle. It goes 6, 4, 3, 2, 3, 4, 6. Then you have pi. Then you've got 6, 4, 3, 2, 3, 4, 6. So there's obviously a repeating pattern there. Let's write it down. The denominators go 6, 4, 3, 2, 3, 4, 6. Then you get pi, and then you repeat. So that's how to name your denominators. I would fill those in first. Then we've got to look for a pattern in the numerators, and that's going to be different in each quadrant. In the first quadrant, so don't put this label all over your work, but here we go. Let's just split up the quadrants. Don't put this on yours. Don't put these labels. In quadrant 1, what do you notice about all the numerators? They're all just pi, 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 pi. So that's very easy. The numerators in quadrant 1 are just pi. Oh, that's right, and this numerator equals pi. Looking at quadrant 2, think about how we worked out this one's numerator, and it might help you notice the pattern. We worked out this one's numerator saying I've got a bit less than a whole pi. And if I've got a bit less than a whole pi, the numerator is just a bit less than the denominator. It's 1 less. 5 is 1 less than 6, 3 is 1 less than 4, 2 is 1 less than 3. And in fact, even for this quadrantal angle at the top, 1 pi is 1 less than 2. Okay? So I think quadrant 2 is the -1 quadrant when I'm looking at numerators. The numerator is 1 less than the denominator, and it's multiplied by pi. So let's fill in this note. On quadrant 2, the numerator equals pi times the denominator -1. Why is it the denominator -1? Because your angle, the angle you're naming, is a bit less than pi. Less than, you're subtracting. Bit less than 1 whole pi. And once you've spotted that pattern, hopefully you quickly notice the similar pattern in quadrant 3. In quadrant 3, all of these angles are a bit bigger than a whole pi. So their numerator is a bit bigger than the denominator. I call this like the +1 quadrant. Get your denominator and add 1. 4 is 1 more than 3. 3 is 1 more than 2. 5 is 1 more than 4. Your denominator is 1 more than if your numerator is 1 more than the denominator, you're in quadrant 3. Your numerator equals pi times the denominator +1. Why is it +1? Because your angle is a tiny bit more than pi. That's why you're adding. And let's look in quadrant 4. This one's much harder to spot, but think about how we got that 11 pi by 6. all of these angles are a little bit less than 2 pi. And to get 2 pi, you get the denominator and you double it. So for instance, this could be written as 12 pi over 6, or it could be written as 8 pi over 4, or 6 pi over 3. The numerator is 1 less than the denominator times 2. Denominator times 2, 3 2s are 6, take 1 off, you've got 5. 4 times 2 is 8, take 1 off, you've got 7. 6 times 2 is 12, take 1 off, and you've got 11. So in this quadrant, our numerator equals pi times 2 times the denominator, subtract 1. Why it's 2 of those, take away 1, your angle is a bit less than 2 pi. Now these rules here only hold for your special angles with these denominators. You cannot use this thinking if you have a denominator like 10 pi. For instance, if you're breaking a whole pi into tenths, every angle that's a tenth up here is not going to be 9 pi over 10. It'd be different. It only works with these special angles, those denominators, okay? Right, so what we would do in my other classes now is they spent a mad minute, trying to remember which one will I use, trying to quickly name these. And this is something you want to practice in your homework. You want to be able to name every single angle going around here in about 40 seconds. Now, I would give you time to practice, but I notice we're already falling a little bit behind in this class. Guys, some of you are really late to class. It holds all the rest of us back. Please try and get here on time. How to fill it in quickly. I'll model it, and then you can practice this in your own time. You start off just with the denominators, and you quickly zip around, just put a fraction bar at every single one. Don't write anything with a fraction bar, name that one pi, fraction bar, fraction bar, fraction bar. And this is 0 or 2 pi, go the whole way around. Now you just quickly go in and put in your denominators. They went 6, 4, 3, 2, 3, 4, 6. 6, 4, 3, 2, 3, 4, 6. Repeat, 6, 4, 3, 2, 3, 4, 6. Now you put in the numerators, just pi in quadrant 1. This is the -1 quadrant. Write a number 1 less than that and stick a pi with it. 1 less than 6 is 5 pi. This is the +1 quadrant. Just write those numbers with 1 added onto them. And in this quadrant, you do 2 times the denominator, take away 1. So 6 take away 1 is 5. 5 pi over 3. 4, that'd be 8, 7 pi over 3. 6 over 12, 11 pi over 6. And you can fit it in really, really quickly, and that's something you need to practice. So you very quickly can name them. And what you're naming is you're actually naming this terminal ray. It's where the rays go. That's what you're really interested in. So you're finding this angle to this ray. Okay? Right. A bit of notes now. Oh, and this is what this thing looks like when it's all fully done. And I've noticed mine's got a mistake in it. That should say denominator plus 1 there. Okay. Back into your notes now. Don't worry about anything that's on this pink part. We don't need it. I don't do it that way. There's formulas you can memorize, but I'd rather you actually understood it and just built it every time. It's much easier in the long run. The main goal of our lesson today is to look at reference angles. What a reference angle is, they're always positive, and we're not drawing them in standard position. So we're not saying if they're clockwise or counterclockwise, they're positive or negative. We just are thinking about an acute angle, and wherever it is, we're not looking at the direction that we drew it. So we're always just going to call them positive. So reference angles are an acute angle formed by the terminal side of an angle and the x-axis. Always the x-axis, never the y-axis. So let's have a look at, if we were given the angle 150 degrees, which in radians is 5 pi by 6, what you do is you draw that angle, so graphic, XY axis, 5 pi by 6, I'm starting to find easy to draw than 150 degrees. It's here. Now, if you were sketching the angle, if you're told to sketch the angle, you draw this on. But what we're really after is this terminal ray. That's the most important part of your drawing. And how you get your reference angle is somewhere on the terminal ray, put a point. Put a point on the terminal ray and bring it down with a right angle to the x-axis, always to the x-axis. Now you just have to work out the size of this angle, and it's called, I call the reference angle theta prime. Theta prime is your reference angle, and just look at the picture. What piece of pi do I need to add to 5 pi to 6 to get to 1 whole pi? In this case, in radians, it would be pi by 6. It's really easy with your special rate angles in radians. It always is just, they have it, it has the same denominator. In degrees, if I was naming this angle in degrees, just think what you add to 150 to get to 180. That's clearly 30 degrees. So let's try this with 5 pi by 3. Quickly do a 2-second sketch and draw me the terminal ray for 5 pi by 3. Look at that numerator. It's not just 1 bigger than 3. So it's not in quadrant 3. It's actually, if you double 3, you get 6, it's 1 less. So we're in quadrant 4. That's my terminal ray for 5 pi by 3. Just by looking at those numerator and denominator. That would be the angle if I sketched it. But what I'm really after here, that terminal ray is called 5 pi by 3, is I want this. This is my theta prime. How you know you've got the right one? Draw a point on your terminal ray and link it to the x-axis. So on this one, what would I have to add to 5 pi by 3 to get to 2 pi? But it's just going to be pi by 3. It's so easy in radians. It's just basically, it's got that same denominator. Okay? Now, why am I talking about these? Why do we need them? Why do we spend so much time building this great big monstrosity? It's because reference angles are supremely useful. Why do we need reference angles? In geometry, you learned that trigonometry was all about right triangles, and you use this thing called SOHCAHTOA. And you can tell someone who kind of started memorizing math and never really understood it because they think trigonometry is about triangles. It isn't. They're stuck in geometry level math and they never got on to really understand pre-calculus and calculus. If you really understand trigonometry, you realize it's not about triangles at all. It's actually about circles. But let's get you to that understanding. So first of all, let's work this from a geometry level, like we're a geometry student. If we wanted to find the sine of 60 degrees, I'm not using radians because we're pretending we're in geometry, we would draw a 30, 60, 90 triangle. We'd work out which was the 60-degree angle, and we'd label the sides. I hope you can do this quickly. This is the big angle, this is the small angle, so this is the short side. This is the long leg, it'd be ugly, and the hypotenuse is double the short side, okay? So we're looking at 60 degrees, and in geometry you learned that sine is the opposite divided by the hypotenuse. You learned to do opposite divided by hypotenuse. Opposite 60, we've got the square root of 3, and our hypotenuse is 2. So you learned that the sine of 60 degrees was root 3 over 2. And in the same way, if you had to do the tangent of 45, actually probably just use a calculator. The tangent of 45 degrees in a 45, 45, 90 triangle, we've got 1, 1, root 2. You need to know these triangles well. And tangent is opposite over adjacent. So it's 1 divided by 1, opposite, adjacent, which gives you 1. Okay? That's how you learn to think about trigonometry when you're in geometry. But when you get to pre-cal, we don't just stick in quadrant 1. We know that there's angles that go to 360 degrees and beyond, and they can be positive and negative and all sorts. So we can't use right triangle trigonometry and SOHCAHTOA, because look what would happen if we did. If I wanted to find the cosine of 150 degrees, and I was in the geometry class, I'd draw a triangle with 150 degrees, and oh, it's not even a right triangle. Hasn't got a right angle in it anywhere. Which is the hypotenuse? Well, it doesn't have one. Okay, so we can't do it that way. We want to move into, so we're not going to think cosine would normally be the adjacent over the hypotenuse, but we don't think about it that way. We're actually going to move ahead and say, right, in real trigonometry, what trigonometry is about, it's about the coordinates of a point in space. It was actually developed by the ancient Assyrians, actually trying to track stars in the sky. That's really where it came from. So if I had an XY point in space, defined by the angle 150 degrees, I want the reference angle, because if I work out this reference angle, this 30 degrees, now I can identify, I've got a 30, 60, 90 triangle, and this point is a certain radius from the center. Okay? So on a 30, 60, 90 triangle, take a second, label both sides. Your short leg is opposite the 30. The radius is double the short leg. And this is vertical, so this will be my my y. This will be my x. And think for a second, what is that x? Did you just write root 3? If you did, your answer is going to be wrong. Why? If I'm in quadrant 2, is my x positive or negative? It's negative. So even though we're using a right triangle to come up with this length, we're recognizing that it's actually an x coordinate in space. And because it's in quadrant 2, the x coordinate is negative and the y coordinate is positive. Okay? But the reference angle helps us to come up with the absolute value of the lengths of those legs. In a circle, a radius is never negative. A radius is always positive. But if you have an XY point, X and Y can be positive or negative depending on what quadrant you're in. So to find the cosine of 150 degrees, I'm looking at the XY position of a point that's a certain radius from the origin. And cosine isn't adjacent over hypotenuse, it's the x divided by the r. So in this case, it is negative the square root of 3. It's your x divided by your r. Please never leave a negative in either the numerator or the denominator. Work out what it is for the whole fraction. A negative divided by a positive is a negative. So I've got negative root 3 over 2. That negative does not belong with the numerator anymore, it belongs with the whole fraction. So let's try this for the tangent of 225. think about what quadrant you'd be in. It's a bit bigger than 180 degrees. It's 180 degrees plus 45. So how to do this? The first thing you do is you draw your terminal ray. That's the most important part. Draw the terminal ray, then identify where your reference angle would be, put a point on the terminal ray, always link it to the x-axis. So now this is my reference angle, and I know my reference angle is this 45. So what I have here now is I've got a 45, 45, 90 triangle. So I could quickly label the sides 1, 1, root 2. But I'm wrong. At this point, my answer is not right yet, because remember, with trigonometry, I've got a point that's a certain radius from the origin, and that point has x, y coordinates. So this x coordinate in quadrant 3, my x isn't positive 1, that would have taken me out here. My x for this is -1. And my y isn't positive 1, that would have taken me up here. And down here, that's -1. So how do I find a tangent? Now you need to remember your letters in the ratio. Remember, tangent is like slope. Tangent is y over x. So it's -1 over -1, which gives us a positive 1. So what we've just covered here is that a reference angle can help us find any trig function of any angle at all, not just angles that would fit in a right triangle. And we're linking it to circles with a radius of r and an xy point that lies on that radius. So let's sketch -150 degrees, find its reference angle, and we'll talk about its trig functions too. -150 degrees, first thing to do is its terminal ray. It would be here. Find its reference angle. That angle there is the reference angle. Our reference angle would be 30 degrees. We don't call it -30 degrees, because that would be the reference angle for any angle that ended here. It would be the reference angle for 210 degrees, which is 180 plus 30, yeah? And it means that we could use that triangle. This was 30, this would be 1, root 3, but negative, and this would be 2. We can use that x, y, and r to find any of the trig functions for -150. We could do the sine of -150 degrees. It's going to be exactly the same as if I'd used this angle, the sine of 210 degrees, because they all have that same reference angle and they're in quadrant 3. Sine is y over r. My y is -1, my radius is 2, so I call that -1/2. I could find the sine, the tangent, the cosecant of any angle that ended on this terminal ray. Any angle that's coterminal with -150 degrees, just by identifying its reference angle and drawing a reference triangle in the right quadrant. Okay? Moving on. Now, this is something special called the unit circle, which you'll hear many people mention. What's special about the unit circle is the number 1. The unit circle is a circle of radius 1. We do not use it at Tompkins. We must be one of the only schools in the nation that do not learn the unit circle. Now, you're going to start thinking that, let me get to it. This thing is the unit circle. No, 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 no. This is the beginning of the unit circle where you just label the points. But people who, when they're talking about the unit circle, it's not just these names of these angles going around the circle. They're thinking of, there's over 100, is it 100? Something like 100 pieces of information or more that go on the unit circle. We're just getting you to learn the angles. They learn a lot more. And at Tompkins, we don't use it for a very specific reason. But if you get a tutor from out of Tompkins, if they've never tutored anyone who's at Tompkins, they're going to probably wonder why you're not learning the unit circle, and they're going to want you to learn the unit circle. Please do not. Make them teach you using reference triangles, at least for the first month. It really helps you to understand what's happening in trigonometry. I've taught this at several different schools. My first 3 years, I taught trigonometry using the unit circle approach, and it works very well for some students, many students, but most students memorize something, they have no idea what it's talking about, and they never really understand trig. Why the unit circle is so powerful and why people like it, because you memorize the coordinates of every single point around this circle as XY coordinates, and look at what happens. If the sine of an angle, if sine is y over r, if the radius is 1, it just equals the y coordinate at any point. If I want to know the sine of this angle, all I need to know is the y coordinate. All I need to know is the y coordinate. If I want to find the cosine of any angle, I just have to identify where the point was. And cosine is x over r. And if the radius is 1, it's just the x coordinate of this point. But it does mean that you really lose track of, and there's a whole bunch of other questions you have no idea what to do, and students get really, really mixed up with their cosecant, secant, and cotangent when they learn it this way. So please stick with the way that we're teaching it. In about a month's time, sometime before the end of the school year for sure, I'm going to tie it together with the unit circle for you, so that if you go on to do math in another school, at least you'll know what the unit circle is, and I'll tell you ways how to memorize it. But please try and stay away from memorizing the unit circle for now, however much pressure other people put on you. Okay, so let's find one of these. Let's do those are all boring. Let's do the secant of 7 pi over 6 using our reference triangles. Secant of 7 pi over 6. The first thing you need to do is draw a triangle in the right quadrant. How you do that is you first of all draw the terminal ray for the angle. 7 pi over 6, the numerator is just a bit bigger than the denominator. We're in quadrant 3. And, oh, you draw the terminal ray. Sorry, I drew the triangle. Draw a terminal ray, put a point on it, link it to the x-axis. And then think about that reference angle. Your reference angle in radians is so easy. It's just the one with the same denominator. Okay, pi over 6, which maybe you already know is 30 degrees, or maybe you're starting to think in that. So this triangle here is a 30, 60, 90. And if this is 30 degrees, this side here is 1, this side here is root 3, and the radius is double the short leg. But I'm in quadrant 3, and I'm not just thinking of that as a triangle side length. I'm thinking of this as an x coordinate. In quadrant 3, that must be minus. Quadrant 3, this y is also negative. Now I can do the secant. Label, identify the triangle, put a length on all 3 sides, and it's either going to be, the only ones we can ask you about are based on a 30, 60, 90 or a 45, 45, 90. We can't ask you about any, without a calculator, we can't ask you about any angle other than those, okay, when we just give you an angle. This angle is either based on 30, 60, 90 or 45, 45, 90. Now, secant is something to do with cosine, so it's something to do with x's the wrong way up. I don't know how you're memorizing that, but I know them that way. So my secant of 7 pi over 6 is simply the radius, that's this, 2 divided by my x, which is negative root 3. And a positive divided by a negative gives me a negative. And I have to rationalize that denominator, so it's going to turn into 2 root 3 over 3. Okay? You need to practice these. We're still really doing the homework that probably would have originally been set for Wednesday. There is a worksheet that you can print off. It's all from the textbook too. If you want to print the worksheet, you can. And try and do the whole of the front of the worksheet for your homework tonight. And we're about half a day behind. And we'll learn how to do the back of the worksheet tomorrow. Okay? I think we're at the end of the class now. Yes, the bell's going to go any minute now. Should we try one more? What else have I got here? Oh, I've got quadrantal angles. Well, we haven't done quadrantal angles. Oops. Yeah? Who's asking me a question?
Anaya.
Hi, Anaya.
Hi. How can you tell if it's either the 30, 60, 90 or 45, 45, 90?
Okay, you just look at the denominators. All you do is you look at the denominators, and this is why you want this brightly colored thing. Yeah? Well, you can't see it so much there on that one. But pi by 6 is 30 degrees, pi by 4 is 45 degrees, pi by 3 is 60 degrees. You see the 3 goes with the 6 and the 6 goes with the 3. As soon as I see any of them, I just look at the denominator and I know what sort of angle I'm looking at. So let's do one of these. Let's do, no, I don't want to do 7 pi by 6, we've just done that. Let's do 4 pi by 3. I see 3, I know my reference angle immediately. Just looking at 3, my reference angle is pi by 3, which is 60 degrees. I'm in, which quadrant would I be in? A bit more than a whole or a bit less than a whole? It's a bit more than a whole. Whole pi, this is in quadrant 3, we're here. And my reference angle here is pi by 3, which is 60 degrees. Now can you label the sides of the triangle? I'm looking at a 30, 60, 90. This must be the 30, so this must be the short leg. The radius is double the short leg, and the y on this one must be the long leg. But I'm in quadrant 3, so my x must be negative and my y must be negative. Okay? But how I identified the angle was just by looking at that denominator. And I know that pi by 3, I'm just looking at that 3, is the same thing as 60 degrees. This is why we really want you to know a 45, 45, 90 and a 30, 60, 90 triangle really well. You must be able to look at them quickly and go, okay, 1, 2, root 3. And this one, 1, 2, root 3. This one, 1, 1, root 2. Because you're going to have to be able to put them anywhere and label their side lengths. This one's cosine would be x over r, so it's negative 1 over 2. It's negative 1/2. Okay? Please do your homework tonight. Don't leave it. Goodbye, guys. And I didn't do quadrantal angles. Ugh, can't believe I haven't done those yet.